Hi class, we are on to chapter 10.6. This is determinants and Kramer's rule. So we've talked about determinants a little bit, mostly in the form of 2x2 matrices. We did say previously that if we want to find a determinant, it has to be a square matrix. Okay, so what we're going to cover in this class, or in this lesson today, is how to find determinants for larger matrices. We have somewhat, to some degree, covered how to find a determinant for 3x3 matrices. We talked about that in the cross product section for vectors in chapter 9. So reviewing that might help a little bit before you get into this section, although it's not really necessary because we're going to really cover it from the beginning, from the basics. What we cover in chapter 9 for the cross product was just enough to get us through that section. So in this section, we're going to cover in more detail exactly what it means to do a determinant for a 3x3 matrix and how to extend that to larger matrices to make it easier to find. Okay, there's a couple of methods in this section that would be really easy for us to use that I'm not going to actually use here. If you want to see some other methods of finding the determinant, you can look at my linear algebra section. My linear algebra playlist. I have a video on determinants, a couple of videos on determinants, but the first video on how to find a determinant in that section goes a little bit deeper into it and has a couple of shortcuts that we're actually not going to go over here, but if you want to look at that section, that might be helpful for you. Okay, so again, in the last section, we had to use determinants of 2x2 matrices in order to find inverses. It was relatively easy to find the determinant of a 2x2 matrix, right? We saw this in the cross product section, and we actually saw this somewhere else in chapter 9 too. I can't remember where exactly, where we go over determinants of 2x2 matrices. It actually probably was the cross product section. 2x2 matrices, very easy to find the determinant of. It's just the main diagonal product minus the secondary diagonal product, right? Remember, the notation is different. If I have straight lines, that represents determinant. Bracketed lines, I guess we could say, represents a matrix, right? So if I'm inside of brackets, it's a matrix. Inside of straight lines, kind of like an absolute value, it means I'm finding the determinant. So it's just the product of A times D minus the product of C times B. Okay, so that's the determinant. We use this to find the inverse of a 2x2 matrix. It's one of the things that we're using. Again, only square matrices have determinants. If we want to find something that's larger than a 2x2, it can be a little bit tedious, okay? So we're going to go over a general method, which expands on the method from chapter 9 in the cross product, that will allow us to be a little bit more flexible in the routes that we take for trying to find the determinant. It might make things a little bit easier depending on our matrix. This method is called cofactor expansion. This is a method that's covered in calculus 3 as well. You will see this again. It will come up again at some point in your studies if you make it that far through your math sequence. Some of you only have to go to calculus 1, but that's fine. This is still very helpful for us. Okay. So for cofactor expansion, it's a way of kind of choosing a row or a column to go down to find the determinant. Before, when we're looking at large matrices, really we only went up to 3x3. We only went along the top row. Using cofactor expansion, we can kind of pick and choose the best option for us to find a determinant. So we can actually go down any row or any column. So let's get into the method, and then we'll talk about how we choose which which route for us is better. Okay. So cofactor expansion. So again, this is the same method we use for trying to find the cross product of two vectors. Cofactors are denoted as Cij because for each element in your matrix, right, each entry, which is denoted by Ij, right, this row, this column, each element has its own cofactor. Okay. The signs of the cofactor alternate. Right, and so we'll talk about how they alternate. They alternate based on a formula, but it's easier to just memorize the manner in which they alternate rather than the formula. Okay, So we have what's called an associated sign matrix, which helps us to remember how it is that it changes. So the way that it works is that the first entry for cofactors are positive, and then negative, and then positive, and then negative, and then positive, and then negative, and so forth, right? The first one is positive. If we go down a row, it goes negative, positive, negative, positive, negative. So it's just alternating in sign all the time. You will never have two signs that are next to each other on the left and right, or up or down. You can diagonally, but never up and down, or left and right. Left and right, they always are different. Up and down, they're always different as well. So it looks like this. So notice if I look at this one, for instance, up is not a plus, down is not a plus, left, or I guess right is not a plus, left is not a plus. But when I go in the diagonal direction, yeah, I can have the same sign. So plus, minus, plus, minus, plus, minus, right? This is a plus, so it goes minus, plus, minus, plus, blah, 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 blah. Right here is minus, plus, minus, plus. It just alternates in sign so that it's always kind of offset by 1. The formula for that is -1 to the power of IAJ. So you might say, how does that help me? Well, if you want to remember it by this notation, which is not useful for us at this point in our math skills, maybe it is, remember that this is the A11 term. So this would be -1 to the 1 plus 1 power. So what's 1 plus 1? 2, right? So this is -1 squared. -1 squared is positive. This would be the 1, 2 position. So this would be 1 plus 2 or 3. -1 cubed is a negative value. Okay, so that's one way to remember it. Okay, is you can use this formula, where easier is just remember this starts at plus, and then you alternate in signs this way, alternate in signs this way, and then as you fill in the rest of the rows, you're alternating signs again, right? Or as you're filling out the columns, you continue to alternate signs. So this is not the cofactor value, but it is the sign that is attached to our cofactor. So we haven't actually talked about how to find the actual cofactors yet, but we do know how to determine what the sign is going to be for the cofactors. Okay. So what we're going to do is, based on what our matrix looks like, we're going to choose either a row to go across, any row, or we're going to choose a column to go down, any column. But we're not going to go down a column a little bit and then a row for a little bit and then a column. We're not going to do that. There is a method that you can use to do that. I personally actually don't know it. I have to look it up. Every time I look at it, it looks very confusing to me. Some people said it's very easy, but I'd have to really sit down and look at it. So what we do is we just go down a single row, or we go down a single column. You do not zigzag around. Okay, there is a method to do that, but there's a lot of extra math that goes into it. We're not really there yet. We're gonna just go down a single column or a single row. Okay, the row or column that we choose is the one that has the most zeros in it. Okay, so if I see a row that has a bunch of zeros, that's what I want to go for. If I see a column that has a bunch of zeros, that's the one I go for. Maybe I see two columns and they have the same number of zeros. Then I'm going to choose the one that has the easiest number. Maybe one of them has a bunch of ones in it, and the other one has like 2 and -5 and 7. I'm going to go with the one with a bunch of ones. So I'm really looking for the column that has a bunch of zeros first and foremost, and then I'm looking for, if there's multiple rows or columns that have the same number of zeros, I'm choosing the one that has the easiest numbers in it. Okay, so that's the next thing. So what we're going to do is we go down the row or that column, and every time I reach a value inside of that row, let's just say we're going down a row, every time I am at a value in that row, I check to make sure my sign is positive or negative based on this, okay? And I take the value that I'm on in that row or column, which we call Aij, and I use that to multiply times a submatrix that's created by deleting that row and that column that entry is in. And then I take the determinant of the submatrix. So we've seen this before. It's just like we did with the cross product, but when we did it with the cross product, we only went across row 1. We can actually do this by going across any row or any column. Okay, so the entry Aij multiplies against my cofactor, which is Cij, and we disregard all entries in the row and in the column, and we find the minor. The minor is the determinant of the matrix that's left when we delete the row and column that our value is in, that we're going down. Okay, so that determinant of the submatrix. So Cij is the minor times that sign, and what we're going to do is we're going to take this value and multiply it times whatever entry is in that position for our sign matrix. Oops. Okay, and we're going to add them all together. Right, so you've seen this before. This might sound confusing, so obviously we're going to do an example or two to make it a little bit easier to comprehend. Okay, all right, so for example, let's find the determinant of this 3 by 3 matrix. Now, just looking at this, there's lots of nice values, a lot of ones here. Even though these are all ones, that's not where I would want to go. So I'm looking for where the zeros are. Okay, so I have a 0 here. When I look at the row that that's in and the column that that's in, that's my options that I want to choose to go across or go down when I try to find this determinant. So if I go down this column vector, we'll have a 0 and there's 1s there. That's pretty nice numbers. If I go across, I got 0, a 1, and a 2. Now 2 is not a terrible number by any means, but multiplying things by 1 is way easier, because notice here, all we're doing is a lot of multiplication. This is the minor. The minor is a determinant of a submatrix when you delete a row and column. So there's a lot of multiplication going on. There's some addition and stuff going on, but no matter what I'm doing, adding and subtracting, multiplying, it's always easier with a 1 than it is a 2. So this column would be an easier choice than going across this row. Okay, so notice that the entry A21, so second row, first column is 0. Okay, so the best choice again is go down column 1, or row 2, right? Remember, row, column. Okay, so we just discussed this as right. So no matter which row or column, the value that I compute for the determinant, it's not going to change. Okay, the determinant of this matrix is the determinant of this matrix. It doesn't change depending on what row or column I go. So that's why I have a choice, right? And that's why column 1 seems to be like a better choice, right? So what I do is I'm going to go down this row, this column, I'm sorry. So when I look at 1, I'm going to use that value, and I'm also going to delete its row and its column, just like we did in the cross product section. And I'm going to multiply this entry times its sign. So remember, we always start with a plus, plus, minus, plus, plus, minus, plus. So this is a plus. So I have a positive 1 times the determinant of this submatrix here. So for this entry, I will have 1 times 3 minus 2, so just 1. Okay, so my minor is this, the determinant of this submatrix, which is 3 minus 2, which is 1. Okay, so my cofactor is negative 1 raised to the power of 1 plus 1 times 1, which is 1, and I would take this value and multiply it times what I have here, which is 1. So no matter what, I'm getting 1 out. Okay, so my determinant, so I'm going to go down this column. So this was just an example. So we found the first value, okay, 1, which is the entry there, times the minor, which is this determinant, right? Determinant of what's left, 1, 2, 1, 3. I have 0, which would be subtracted, right? Plus, minus, plus. So I'll go minus 0 times, and then I delete its column and its row, and I look at the submatrix, right? So minus, and that's based on the sign, 0, which is the entry, and the submatrix, 1, negative 1, 1, 3. But it doesn't matter what this is, because I'm multiplying it times 0. That's why we like to go where zeros are. Okay. Then I will add 1, and it'll be positive, because it goes plus, minus, plus, right? So that's why the 0 is being subtracted, because it's in the subtraction. So plus, minus, plus. Here, I'm going to erase this row, this column, and this is going to be the determinant of the minor. Okay, so plus 1 from here, and the minor matrix is 1, 1, negative 1, 2. 1, 1, negative 1, 2. So looking at these and actually computing these, I have 1 times 1. Okay. 0 times, I actually computed for you guys, but I don't really need to, right? But this is 3 minus a negative 1, so this should be 4. Okay. Plus 1 times 2 minus a negative 1, so 3. So I have 1 plus 3, or 4. And if I went down any other row or column, I would get the same thing. Now if I chose this one, for instance, I'd have to multiply a bunch of stuff times negative 1, 2, and 3, and then changing their signs as appropriate. But it's easier when there's a 0 there, right? Because then I actually only have to do this math and this math. So again, let's say that we went across row 3 instead, 1, 1, 3, just for posterity to show that it would be the same thing. So remember, plus, minus, plus. Okay. So I have 1, so that's from here. So I delete this row, this column. This is that submatrix left over. Okay. I'd have a negative 1. Delete this column and this row, and you get 1, 0. Negative 1, 2. Okay. This would be plus, right? Plus, minus, plus. So plus 3. Delete this column, this row, and this is the sub matrix. Right? So then compute that. This is a 1, right? 2, or I'm sorry, this is a 3. 2 minus a negative 1. It's a 3. Minus, so this will be 2 minus nothing. So minus 2. And then this will be 3 times 1 minus nothing. So 3. You end up with 6 minus 2, which is the exact same thing we had before, 4. So it doesn't matter what row, what column. So last time you noticed we went in a column. This time we went across a row. When I don't write all this extra stuff here, it's pretty clean, right? Just remember to change the signs as you go, according to, you know, this one being plus. And then erase the row, erase the column, find the next determinant. 3x3 matrices are not too bad. A 4x4 matrices, notice if I had an extra row and an extra column, when I delete an entry, I'd be left with a 3x3 matrix. So if I went down 4 times, I would have to do this 4 times, because the determinant of a 3x3 gives me 3 different calculations. So if I have 4 entries in a row or a column, I'd have to do this 4 times, because every time I went down an entry, right, delete the row, delete the column, I'd be left with a 3x3 matrix. So then I'd have to do this again on that 3x3 matrix that's remaining. So when you get into very large matrices, the number of times you have to kind of sort of like nest these things gets very large. So notice we had a 3x3. I did this 3 times. If I go, so when I say 3 times, I mean I have 3 determinants, 3 subdeterminants I have to find. If I had a 4x4, 4 times I'd have to do a 3x3 determinant. So there would be 12 matrices I'd have to do. So I'd have to do this 4 different times. So then I'd have, that's a lot of math, right? So just going up by 1 dimension, 1 row, 1 column, creates a lot more math. So we'll talk about how to deal with even larger systems. This works for every size square matrix, but when you start to get larger in value, it can be very, very time consuming. Okay. So again, when we have a larger matrix, we have to continue to find determinants of large submatrices for our minors, right? So for example, if I have a large, this isn't even a large matrix, right? It's just 4x4. It's 1 more dimension. If I need to find the determinant, okay, so notice I have 2 different options, either row 2 or column 3, because they both have 2 zeros. So this has 2 zeros going down this row. This one has 2 zeros as well. They both have a 1 and a negative 1, so it doesn't really matter which one I decide to go down. Okay, so let's say we go down column 3. So for my first entry here, so plus minus plus, so I have a negative 1. Delete this row, delete this column, and I have a 3 by 3 matrix left. Okay. Luckily, there's a lot of zeros, so I don't have to worry about what happens here, because no matter what I get, it goes to 0. So I go to my last entry, so plus, minus, plus, this will be a minus, that's why you see a -1. Delete its row, delete its column, and then notice I have a 3 by 3 submatrix. So now I have to expand these, and I get to do the same thing. I choose which row or which column I decide to go down. Okay. So let's say we go down column 1 for both, because both of those have a 0. I'm staying consistent in both. It's fine. But I could just, for this one, go across this row instead, and go across the second row for this. But since the 0's in the same place, right, it's both in the first column, we'll just go down the first column. So for this one, I have -1, plus this will be minus. I do not go plus minus based on the original, because this is the determinant I'm finding. So this is plus, this is minus. So now I have a -1 times another -1. Okay. Well, here I'm taking the 0. And so if I take this away and this way, this is the 2 by 2 I have left. Okay. So it doesn't matter, it goes to 0. This one will be negative. Delete the row, delete the column. I'm left with 1, -1, -1, 1. Okay. So plus, minus, plus. So I'll have another -1, and I'll have this as a submatrix, 1, -1, 1, -4. Okay. So then I got to compute that, and to that I'm going to subtract 1. Okay. And I will have a large matrix. I'm going to use this. This is plus. Delete the row, delete the column. This is what's left over. So plus, this will be minus, so -0. And then I'll have, this is plus, so plus 1, 1, 4, 1, -4, right? 1, 4, 1, sorry, -1. So then I gotta do this. So now I'm working inside the parentheses. So this is 0. I find what this determinant value is. I find what this determinant value is. I find this determinant value. I find this determinant, right? So this is 1 minus 1. So this will be 0 also. So 0 minus 0. This will be -4 plus 1. So this will be a -3 times this. This will be a -4 plus 1. So this will be a -3. And this will be -5. Okay. So here I'll have -1. This is just 0. This is -1. Remember, this goes to 0. This is 1 minus 1. This will be -1 times 3, -3. So this is -4 minus a -1. So that's plus. So that's a -3. Then I'll have, and that'll close up this bracket. Okay. Then I'll have a -1. This is -3, like I said before. -4 plus 1 is -3. Minus is 0, so I won't include that. And this will be -1 minus 4, so this will be -5. Okay. -0. And plus 1 minus 5. So you see what I'm saying? We have to like nest. So just imagine if these weren't 0. Imagine if I had no zeros in this at all. I would have not just these two that I'd have to compute, right? This one times a 3 and this one times a 3. I'd have another 3 by 3 and another 3 by 3. And then I'd have to go in and do all of this for those as well. Okay. So luckily this one was nice to us. And I can just simplify this. So this is a +3. This is nothing. +3 times a -1 is -3. This is a -5. This is a -3. So together, that's -8 times a negative, right? So I have -8 here, -3. I'm going to add those. I'll get a +5, right? This turns into +5. Sorry, +8. This turns into -3. +5 left. So that's how we do a larger matrix. A lot of work, right? You're kind of nesting yourself in to doing determinants of determinants of determinants. So here I'm trying to find the determinant of a 4 by 4. I end up having a sum of determinants of 3 by 3s. I break that down. I end up with a sum of 2 by 2 determinants, which again, if I had these other two entries here, I would have had 1, 2, 3 here. I had 1, 2, 3 here, right? So far that's already 6. Note, remember, these are 0 because there's zeros in here. Okay, but there would have been one to calculate here. I calculated 1, I calculated 1. And that's just from the first one, right? The second one also would have given me 3. Okay, 1. This one that was 0, I would have had to calculate if there was a number here that was non-zero, plus another one. And then again, if these were non-zero, I would have had 2 more. So that would have been 3, 6, 9, 12, right? So I would have had then 12 determinants, not the best, funnest time. So how can we do that a little bit easier? What's an easier way to do this rather than like just trying to find the best zeros? Because again, they don't always give you zeros here, right? This is me being nice and finding a nice example. So there is one row operation that we have that will not change the value of the determinant. The other row operations we have will affect the determinant in some way. We're not going to get into it because that's more of a linear algebra course kind of thing, but we're going to talk about one that we can use over and over again. It's actually the most useful one. It's the one we use the most, and it won't change the value of the determinant. And so if I take one row and add to it a multiple of another, the determinant does not change value. So really, if I have a large matrix, what I really want to do is I want to try to reduce it as much as possible to reduce echelon form to a triangular matrix. If I can do that, there will be zeros everywhere. Okay? And as long as I can do that without swapping rows and without multiplying a row times a constant, I should do pretty well. Okay? So again, I'm trying to introduce zeros as much as I can by adding a multiple of one row to another row. So let's do the previous example that I did here. And this is already 1, so that's great. So let's get these entries below it to be 0. So in order to do that, I will take this row, and to it, I will subtract this row. Okay. And to make this entry a 0, I will take this row, and to it, I will add the first one. So the first 2 rows will stay the same. This should become a 0. These values will change. This will become a 0. These values will change. Notice I'm not swapping rows. I'm not saying, oh, I'm going to multiply this times 3. I'm just going to take this and add or subtract the other one. Now, the one that I'm using to add or subtract to eliminate, it doesn't matter if I multiply that. But if I take the row I'm on and say, I'm going to multiply this times 3, and then I do stuff, that does actually affect my determinant. So doing these kinds of operations will not. So right away, it's nice because it puts us, just those 2 operations, puts us into a triangular matrix. Even if it didn't, and I just had zeros here, that would be a huge start for me. Okay, so I'm in a triangular system now, right? So I'm going to go ahead, I'm going to use one that has the most zeros. That would either be this one, this column, or this row. Now obviously this one is best because it has a 1, so let's traverse down this, plus, minus, and find all of these subdeterminants, right? So erase this, and I will have this 3 by 3 left. Okay, well, look at that, it's still triangular. So in this one, again, I'm not going off of what it would be here. I'm going off of here, plus, minus, plus. To finish this one out, I will take this one out and this one out, right? This column, this row, and I'll find the determinant of this sub matrix. So I have 1 times this sub matrix here. Well, look at the sub matrix here. It's actually very easy. It's 5 minus nothing. So I actually get 1 times 1 times 5. Notice also, okay, just a heads up, if you get this into a triangular form where it's all zeros under, you can actually shortcut this and just multiply all the entries in your main diagonal. 1 times 1 times 1 times 5 is exactly what we ended up with here. 1 times 1 times 1 times 5. Okay. So, how is the determinant and A inverse related? So we saw in the last section with inverses how the determinant was used to find the inverse of a 2 by 2 matrix. Okay, so it should be no shock that the determinant is useful for finding the determinants of larger matrices. Okay, so we're not going to really get into it in this section for how to use the determinant to get it to find the inverse of a large matrix. It actually is a lot of work, so we're not going to get into it in that. That's, again, would be part of a linear algebra course. If you are interested in it, you can look at my linear algebra playlist for the determinant section. We go really deep into the determinant there. If you're interested, I'm sure that you're not at this point. You're trying to get through the course, so don't worry about it if that's the case, right? What we do like the determinant for, however, is the determinant tells us all kinds of stuff about our system of equations, especially if, well, it has to be a square, right? So it's very useful. We're not going to get into it too much because, again, that's not the point of this. But it is useful for determining whether or not an inverse actually exists. Okay, so a lot of times finding the determinant is a lot faster than computing the actual inverse of a matrix. So if I need to know whether or not I can find an inverse and solve a system, sometimes it's just easier to compute the determinant of that coefficient matrix and say, well, the determinant of this thing is 0, so there is no inverse, so I can't solve it, right? There's no solution, basically. It's a good way for me to know when there's no solution to a system, okay? It's not invertible. So we can, not only can we use the determinant to say when there's no solution, but we can actually use it to find the solution of a system without actually finding the inverse, okay? This brings us to what's called Kramer's rule. So just so that we're kind of clear for this section so far, we have talked about several different ways for solving a system of equations. In the very beginning, I said you can graph them if they're lines. It doesn't really work when you're in a 3x3 because you'd be plotting lines in 3 dimensions, really planes, right? So that'd be kind of hard to do. But you can graph, if it's 2x2, 2 equations, 2 variables, you can graph it, okay? For any size system, you can use substitution, you can use elimination, you can do Gaussian elimination, right? Put it into a matrix and simplify it down and use back substitution. That's the Gaussian elimination. You can use Gauss-Jordan elimination, which is that forward and backwards phase, right? So you get it down to the triangular system, and then you try to make everything above the main diagonal 0. We saw that we can use inverses to solve when it's a square system, okay, which is very useful. And now we have Kramer's rule. So we have like 4 or 5 different methods for solving systems of equations. Before, the only option we really had was substitution and elimination. Now we have a bunch of different methods. So again, this is one of the benefits of learning linear algebra in matrices because it makes things a little bit easier to work with once we understand it really well. So let A be a square matrix that has an inverse, okay, and that its components can create a system of equations that have the form A times X equals B, okay. The solutions of this system of equations given by A have solutions of determinant of AI divided by determinant of A. AI, okay, so xi is talking about which column vector we're looking at. So x1 is the first solution, x2 is the second solution, x3 is the second solution. So for instance, if I have a 3x3 system, I have 3 variables. The first solution, x1, right? Second solution is x2. Third solution is x3. Those solutions are given by determinant of AI over determinant A. So what is AI is the question, right? A, I know what it is. AI is our matrix A where we replace column I with the vector B. Okay, so that can be a little confusing. So we're going to do an example so that this makes sense. Kramer's rule is pretty impressive. It's very useful for us to find answers. So again, AI means that I replace, if the A1 for instance is me replacing the first column with my vector B. A2 is me replacing the second column with my vector B. And all the other columns stay the same. And each time I find the determinant of that. Okay, so determinant of A I only have to find once. And then depending on how many columns I have, n columns, is how many times I have to find the determinant. So I actually end up finding the determinant n plus 1 times. N times here for each of those variable answers, and then 1 time for my matrix A in general. Okay, so let's do an easy system. Okay, so let's say that this is my system of equations. 7x1 minus 2x2 equals 3, and 3x1 plus x2 equals 5. Right? So using Kramer's rule, we first need to break this down into a matrix equation. Okay, so I have A, X equals B. We saw before we can solve this by taking the inverse of this and multiplying by the inverse on the left side on both sides of the equations, right? The left side here and the left side here. And that'll give me my solution. That was one of the methods that we learned last section for solving systems of equations. If I don't want to find the inverse, okay, maybe 2 by 2 is not hard to find inverse. Let's say this was like a 3 by 3 or 4 by 4. Maybe it's faster for me to find the determinant by using this method that we used here, using row operations. Okay, I did one set of row operations, and then it was very easy for me to find the determinant in this case. A lot faster than it was to find it for this 3 by 3 here, or I'm sorry, the 4 by 4 here, by going the long way. Okay, so we can shortcut stuff by using row operations, and that might be a lot faster than trying to find the inverse by hand, right? So the determinant of A, this thing is 13, easy to find. That's 7 minus a negative 5, so 7 plus 5 is 13. Sorry, 6, my bad. 7 plus 6 is 13. A1 is me replacing 7, 3 with 3, 5. So you hear 7, 3, negative 2, 1. It's not the same here, right? I replace my first vector with that B vector. So I have 3, 5, negative 2, 1. I'm going to find its determinant, very easy for 2 by 2s. That is 3 plus 10, so that's 13. Okay. I'm going to find, so my answer for x1 then is 13 over 13, right? This is the denominator. What I just found was the numerator, so that's really just 1. Okay. So x1 is 1. I'm going to do the same thing. 7, 3. I replace the second column with B. Okay, so it was negative 2, 1. I replace that with 3, 5. Okay, find its determinant. That's 35 minus 9, or 26. So remember, I put determinant of A2 over determinant of A. So that's 26 over 13, which is 2. So then my solution is 1, 2. Okay. Very, very straightforward. The math was pretty easy, right? So the next part is the area of a triangle. We're just going to go over the formula rather than the full example here, because we've done lots of determinants already. The determinant is really useful for me to find areas of geometric figures. So the only one we're really going to cover right now is the area of a triangle. So let's say that on a graph we have a triangle given by the vertices of 3 points, right? So you'll be given 3 points, and those 3 points are the points of your triangle. Okay. If I want to find the area of the triangle, then I take 1/2 times the determinant of my points being vectors. So x0, y0, x1, y1, x2, y2. And I need it to be square, so I'm going to replace it with 1 for the last column. Now you see here I have plus or minus because the determinant is allowed to be negative, right? So my determinant is negative. I choose this to be a negative 1/2. So I have a negative times a negative, and it's positive. Remember, area is always positive. So if this came out to be negative, I need to multiply it by a negative 1/2 so it stays positive. Okay. So this is what it looked like. Say that this is my triangle. It's not a right triangle, so it's hard to find what the area is. So instead of sitting here trying to measure a bunch of stuff, we can just throw it into here and find this determinant. And that's a lot easier method.